are to design an anti-reflective coating for a camera lens. The lens itself is made of glass, index of refraction 1.5, and the coating material will have an index of refraction n equals 1.35. What minimum coating thickness would prevent reflections of light whose wavelength in vacuum is 500 nanometers? Note, assume that the light enters the lens at normal incidence. For thin film interference, we draw a figure in which the light comes at normal incidence. We draw it at nearly normal incidence to make the figure clearer. And one portion of the light reflects the top surface. Some of it will transmit through that surface, reflect off the bottom, and as a result you'll have two light rays leaving the surface at the top, and these two will interfere with one another either constructively or destructively. The first step in a thin film problem is to decide how many flips happen as the light rays are reflected. The first reflection is at the top surface, and what we notice is that since the material we were reflecting from has a higher index of refraction, we will have a flip of phase during this reflection. The second flip is at the bottom surface, and once again, since the glass is 1.5 and the coating is 1.35, the material we are reflecting off of has a higher index of refraction, and so this means that once again there is a flip of phase at this boundary. Therefore, we have 2 flips total, which is an even number of flips. The problem has asked us to make an anti-reflective coating. Therefore, we would like to prevent reflections, meaning that we wish to have destructive interference between the two light rays. This means we have to consult our table for thin film interference and select the row of even number of flips and the column for destructive interference. That table is shown here, and obviously we will need to select the first row, second column in order to satisfy the condition for the problem that we've been given. This selection yields multiple possibilities for the equation that we need: the half lambda possibility, the 1.5 lambda over n2 possibility, 2.5, and so on. We need to once again consult the problem in order to decide which of these is appropriate. And what we notice is that we have been asked to find the minimum coating thickness. The minimum coating thickness means the smallest value of d, and therefore the formula that we need is that twice the thickness of the film should be equal to half the wavelength over n2. Given that the wavelength of the green light is 500 nanometers and the index of refraction of the medium is 1.35, we're able to easily solve for the distance d, and we come up with a result of 92.59 nanometers. In a real camera lens, actually many layers of thin film coatings are applied to try to prevent reflections across the wavelength of visible light. These kind of coatings are also used in glasses.